Dear students, today let us see Macaulay's method. It is a method for finding the deflection of beams. It is also called method of singularity function. In order to find the deflection at any section of the beam, we need to know the bending moment at that section. So let's see what this Macaulay's method is. In Macaulay's method, a single equation is written for bending moment for all the portions of the beam. And the specialty of this equation is that the equation is formed in such a way that the same constants of integration are applicable to all the portions in the beam. Macaulay's method is also a type of double integration method, but here we need to follow some rules in applying Macaulay's method. Let us now see what are the rules to be followed while applying Macaulay's method to find the deflection at any point in the beam. So the first rule is regarding the selection of origin. Okay, we'll consider two cases. One is of a cantilever and another one is of a simply supported beam. So first let me draw the cantilever beam. Okay, it has one end fixed and other end free. Now I'm applying a point load at the end, two UDLs and again a point load. Okay, so first point load be P1, second one be P2, then W1 and W2 be the UDLs. Now, so these are the four loads applied on the cantilever beam. Here I'm taking the free end as the origin because if we take the fixed end as the origin, we need to find out the reactions and resisting moment at that end, which is a difficult task. So for convenience, I'm taking free end of the cantilever beam as the origin. Okay. So whenever we consider cantilever beams, the one which I have marked with red X is not to be taken, but the one with green tick is to be selected. So I am removing the difficult method or the difficult selection of origin, and I am keeping only the right selection of origin here in the case of cantilever. Okay, now let us consider a simply supported beam. Here you can see two point loads and a UDL, and you can see the reaction at the supports also. In this case, conveniently we can take extreme left as origin. That is x is equal to 0 is the origin, which is extreme left of the simply supported beam. Okay, you can see there two point loads and a UDL and the two reactions. Now let us see the second rule or the second condition to be followed while using Macaulay's method. That is, select a section considering maximum number of loads. So when you select a section to find its bending moment, we need to consider the maximum number of loads. Here also I am showing two examples, one of a cantilever and another one of a simply supported beam. Okay, I am drawing the cantilever beam now with a point load at its free end, another UDL, then again another UDL, okay, and another point load also. Now here the total number of forces are N. It is denoted by the N. We have P1, P2, W1, W2 and the reaction at support. So there are totally 5 forces. So now let's see how to select a proper section. Starting from the free end, if I am taking this section XX, you can see that there is only one load, that is P1, towards the right of the selected section. Again I am taking two more sections named XX. Okay. Now if you have a look at this sections, you can see the extreme right section. Towards the right of that section there is only one load, and towards the right of the second section there is only 3 loads. But if you take the extreme left section, which I am now marking with green, towards the right of the section maximum number of loads are there. That is 5 minus 1, 4 loads. Now let us consider a simply supported beam, okay, with 2-point loads P1 and P2, and reactions at supports are R1 and R2 and a UDL. Now here we are taking extreme left as the origin. So in this case, when we select a section, okay, here I'm selecting a section at this region, I'm marking it with green color. Now you can see towards the left of this section there are the maximum number of loads. We are only excluding R2 here. So this is how we need to select a section that is considering maximum number of loads. Let us now move on to the third condition. Okay, follow the sign conventions while writing the bending moment equation for a selected section of the beam. And that bending moment is generally denoted as m suffix x. As we all know, the sign convention is if the bending moment creates a sagging effect, it is positive bending moment, and if the bending moment creates a hogging effect, it is negative bending moment. Next rule is related to beams with moments or concentrated moments at any point on the beam. So here I am taking the example of a cantilever beam of length L and a point load at the free end and a moment, that is a concentrated moment M, at a distance B from the fixed end. Now let me select a section XX at a distance X from the free end. Now let us see how to write the bending moment equation for the selected section. So let us write mx. The moment due to force P is force P into perpendicular distance x, and it creates a hogging moment, so I am putting negative sign. And this concentrated moment M is also creating a hogging moment, so I am putting minus M here. As the M in this equation does not represent any position, we are rewriting the equation again and including another term, that is the distance of M, that is x minus a, from the selected section in the equation. But multiplying moment with a distance is technically not correct. So what do we do here is, so let me do a small adjustment here by giving a power 0 to the x minus a term. As we know, any term raised to the power 0 is equal to 1. So here we are adding an x minus a term with the moment. In Macaulay's method, it is very important to include this x minus a term. So here we have the fourth rule. The x minus a term has to be included in the bending moment equation when considering moments or concentrated moments at any point on the beam. And here we provide a power of 0 to the x minus a term, that is x minus a power 0, so that the equation becomes technically correct. Now let us see the fifth rule. It says for any term when x minus a is less than 0, that is when x minus a term is negative, that term is neglected. Now I will take the example of a cantilever beam. So here I am drawing a cantilever beam with a point load P at its free end and a concentrated moment M at a distance A from the P and a B from the fixed end. Now I am selecting a section XX at a distance x from the free end and writing the bending moment equation at that section. The moment due to force P is P into x, that is hogging, so minus sign. Now the moment m is considered here as minus x, and it is at a distance x minus a from the selected section. And now we are putting the power 0 here. Let us name the important points in the beam as A, B and C. Okay. So in the region between A and B, the value of x minus a will be negative. So in this region, the x minus a term can be neglected. Hence the term beyond the partition line can be completely neglected. Next, the sixth rule is about how to integrate the x minus a term. Okay, the quantity x minus a should be integrated as a single term, that is integral x minus a power n dx should be equal to x minus a the whole power n plus 1 by n plus 1, and not the conventional method, that is x minus a power n dx integral as equal to x squared by 2 minus ax. That is not the way to be used in Macaulay's method. Now let us see the seventh and the last point. It is regarding UDL. Once a UDL is considered in a section, it must remain throughout till the end, that is up to the final condition. And this can be done by using dummy UDLs. To explain this condition, I am taking the example of a simply supported beam with a UDL W on it. Now if I am selecting any section XX at a distance x from one of the supports, the UDL should not break in between in the case of a Macaulay's method. So what we do is we need to extend the UDL up to the end of the beam. But what happens here is the loading condition is changed now. So we need to do something to cancel out this additional UDL. So what I am doing here is applying the same UDL from the bottom of the beam also, so that we are adding a positive UDL and a negative UDL, and it cancels out. So the net effect of this UDL is 0. Now let us see the summary of this video. In Macaulay's method, a single equation is written for bending moment for all portions of the beam. Compared to the other methods to find the deflection in beams, it is a versatile method to find deflection at any section of the beam when the beam is subjected to multiple loads. In Macaulay's method, we also saw there are certain rules and conditions to be followed while developing the bending moment equation. Let us now see a summary of all that. So first rule is about selection of origin. Second is about selecting a section considering maximum number of loads. As per the third rule, follow the sign conventions while writing bending moment for a selected section in the beam. The fourth point is about the x minus a term, which has to be included in the bending moment equation when considering concentrated moment at any point in the beam. And in the fifth condition, it says that any term where x minus a is less than 0 or negative, that term can be completely neglected. The sixth point says how to integrate the x minus a term. It should be integrated as a whole and not separately. The final point is about UDL. Once a UDL is considered in a section, it must remain throughout. To make it possible, we use dummy UDLs.